So let's code this. And firstly, we're going to import NumPy as MP so that we can use some of its functionality. And then we're going to import Torch to perform our numerical computation efficiently and create our computational graphs. And then from torch.autograd, we're going to import variable so that we can calculate the gradient of our cost with respect to anything that we want automatically. And we're going to plot our two-dimensional data against the output in space, and we're going to plot our cost against time. So to do that, we're going to import matplotlib.pyplot as plt so that we can plot whatever we want. And to plot a 3D graph, we're going to need to import 3D axes from mpl toolkits.mplot 3D, and that import is called axis 3D. So we're going to define some hyperparameters of our model, and these are going to be the number of epochs, so how many times we want to run through the whole data set during training. I'm going to define the learning rate, so what is the relative size of the steps that we want to move our variables in the direction that reduces the cost every iteration. And for this example, we're going to make some fake data set. So we're going to say that it's got n equals 2 features, so let's say number of windows and number of rooms in a house. And how many houses do we have? Let's say m, our number of training examples equals, let's say 300. Then we're going to create x as a variable. So this is going to be our feature tensor, which is going to contain a random set of numbers, and that's going to be m by n. So this is going to be a tensor which has each row representing a training example and each column representing a feature of that training example. So the columns will be 300 and the rows will be 2 windows and rooms. And then we're going to create another variable y, and that's going to contain our made up function for what the price of the house is from the input features. So let's say that the price of the house is equal to 2 times the number of windows, so x, we don't want the data from it, so we're going to call x.data, the number of windows, plus maybe 3 times x.data, so the number of rooms, we want all of the columns and the first feature, plus some bias, because even if the house has 0 rooms and 0 windows, it's still going to be worth something for the land. And so let's say we create a figure to show our data in space. We're going to put this on here, and we're going to create an axis on that figure. Let's call it ax1 equals, so let's add a subplot to the figure, and this is going to be in the position, for now let's just say there's going to be one plot high, one plot wide, and this is going to be the first of those plots. This is going to be a 3D plot because we want to plot our two-dimensional input data against the price, so projection equals 3D. And then we're going to say, okay, ax1.scatterplot, x.data, we're going to plot x.data, all of the rows, the 0th feature, and on the next axis we're going to plot all of the rows, all of the first feature, and then we're going to plot y, and we want the data from that, and we want all of the rows. And for this we're going to say x1.set x label equal to windows, and we're going to ax1.set y label to the number of rooms, and ax1.set z label to the house price. And then if we do plt.show, then we can see our data in space. And this is the data that we've made up and plotted against house price here. And so this plane is what we want to try and fit our linear model to regress the house price with. So we want to see our hypothesis change against time. So we're going to turn on interactive mode, put that up here. We're going to say plt.ion, interactive mode on. And we're going to want to plot not just our data in space, but also a graph of our cost against time. So we're going to change this subplot. Instead of being one axis high, one axis wide, we're going to make it two axis wide. This is still going to be the first axis. And for this one, we're going to need to add in something to make a mesh which covers the whole input plane for our data. So we're going to make two vectors, x1 is numpy function a range, that goes along two numbers, so that's going to create a vector, two numbers long, or up to two, and then we're going to create another one, mp.arange up to 2, just so it's got two numbers in as they increment by 1, and then we're going to create a mesh from this. So we're going to use x1, x2 equal to np.meshGrid. And this is a function which returns two matrices from two vectors, x1, x2, that when you combine the same elements from each of those matrices, they give you every possible point on the input plane as coordinates. And okay, so we're gonna move above this plt.show, and we're gonna add another set of axes. So ax2, let's call it, equals fig.add subplot, and this is gonna be again one high, two wide, and this is gonna be the second graph on that figure. Then we're gonna say ax2.set underscore x label to iteration. I'm going to plot our cost against iteration, so ax2.set y label to cost, and we're going to set the limit to the number of epochs we've got, so ax2.set xlim from 0 to the number of epochs that we're going to go over, and we're going to add a grid to this. And we haven't plotted anything on here yet, but it will change as we update our plot, and we're going to program that later. So now we're going to define our model in a class. And we're going to say that we're going to create a new class called linear model. And this is going to inherit from a PyTorch module, which allows us to train our models using backpropagation. And it allows us to use a lot of other neural network functionality from the Torch class. So our linear model is going to inherit from torch.nn.module, which has some useful features. And we're going to define the class constructor, so def double underscore init underscore self, because this initializer acts on this instance of the class, which is why it's got self. And so in the initializer, we're going to call the initializer from the parent class, so super, we're going to call it from the parent class. So we're going to call init from the torch nn.module, so that we construct our single layer neural network with all the functionality we need, like creating a state dictionary of variables and storing the gradients. And then we're going to define also in this initializer some attributes called linear, which is going to be equal to the torch function linear with a capital L, which creates a linear layer in our network. So that takes two inputs and gives one output. And so what we've done here is we've defined a constructor class within our new, or constructor function within our new class, which calls the parent class's initializer and then also adds gives this instance of the class an attribute linear, which is equal to the torch function linear, which creates a linear layer in our network, which takes 2 inputs and gives 1 output. And so whilst we're doing this, what this is going to create is some variables in our state dictionary. So it's going to create a bias and 2 weights by which these 2 inputs, our number of windows and number of rooms, are multiplied, and the bias which is added to that. And so we'll access that later using a function called get state dictionary, so that we can see what's inside. And so the next thing we're going to do in our class is define another function, forward. So when we want to pass our data forward through the model, it's going to act on this instance of the class, and it's going to take an input x. So it's going to take the number of rooms and the number of windows and the number of rooms that we give it as an input. And so what we're going to do is say that our prediction is equal to this instance of the class's function linear when that acts on x. So when you perform a linear combination of the inputs and add a bias, then that's what the y prediction is. So and then we're going to return the y prediction of this function. That's what we want to get back. And we're going to create, now we defined our class there, so what we're going to do is create an instance of that class. So we're going to create our model. That was just the framework for it. Now, here is where we actually make it. So we're going to call our model, let's say M, that is equal to an instance of the linear model class, which is going to have all of these functions available for us to use, as well as these from torch.nn.module, which are our class inherited from. And so for our model, we're going to define our criterion, which is going to say, okay, what are we trying to maximize? What's our measure of how good our model is? So that's going to be torch.nn.mse loss, which is our mean squared error loss. And so we want to compute this for the average over all of the training examples rather than the accumulative. So we want to create the average be true. All right. And then we're going to define our optimizer, which is going to be equal to torch.optim.sgd. So this optimizer is equal to a function which performs stochastic gradient descent, SGD. And what's it trying to optimize? It's trying to optimize m.parameters, which is what's stored in the state dictionary of our class. And we're going to have the learning rate equal to the learning rate which we specified earlier. LR here earlier is a keyword argument, and LR here is a variable which we've defined. And so we want to track our costs over time. So what we're going to do is create an empty list called costs, so that we can add our cost to it every iteration. And now we're actually going to train the model. So what we're going to do is we're going to say for epoch in range epochs, so that's going to go over this training loop, the number of epochs that we've defined, which I think was 100 up above. And so every time we go through this, we want to say our prediction of y is equal to m when we call x. So that's going to call the forward function and return us our prediction. And then I'm going to set our cost equal to, so criterion, so this is going to perform a mean squared error calculation between our predicted values and our actual output labels. And then we're going to add that to the list which we just created. So costs dot append, and we're going to add cost. So we're going to add the variable cost, which is our measure of our current mean squared error, to our empty list at the moment, costs. But we don't just want cost, because cost is a variable object. We actually want the data from inside it, so we want that tensor to be added to the costs. But it's actually just going to be a scalar. And then we're going to print, as our model runs through every iteration, we're going to print our epoch. So what epoch are we on? We want to know that. So let's print the value of the current epoch, and we want to, and we also want to know the value of the cost at the current moment. So we're going to say cost.data. We want to print these two things, and we want the zeroth object from it, because we don't just want So we have to call data because we don't want the variable object, and we have to call 0 because we don't want the tensor object, we actually just want the number inside it. And then we're going to make our optimizer set the gradients. It's calculated currently equal to 0, because if we don't, it'll add them accumulatively every iteration rather than set them to what they're equal to. And then we want to calculate our cost. Well, sorry, no, we don't want to we're not calculating our cost there. What we're doing is calculating the rate of change of our cost with respect to each of the variables and parameters in our model, so that we can optimize them. And then, so the parameters inside our model now, they basically just exist inside the state dictionary of the model. So that means that we don't actually have them stored as a variable. It's just something that the class is doing automatically behind the scenes, which is why PyTorch is good as well, because it means we don't need to worry about creating these objects and extracting information from them. We can just get them from the state dictionary. But in this case, we actually do want to know what they are, so that we can use them to plot our hypothesis surface against our data in three-dimensional space. So what we're trying to do is get a list of two things which contain the first element as the weights and the second element as the biases, and then we're going to set them to these variables w and b, so that we can use those variables to plot our hypothesis surface. So basically, in the state dictionary of our model, there are two things. There's a weight tensor and a bias tensor. And when we iterate through the for loop here, iterating through the elements in our state dictionary, that variable tensor and the bias, the weight tensor and the bias tensor, then we're getting out our names as our value, their names as our value for I. And then we take that name, I, and we index the dictionary with it. So we say from our model in the state dictionary, get the weights or the bias, which is I, and then take the 0th element from it to get the actual values from it. I get the first row from it. So that's what we're doing there. And that gives us our values of w and b as variables. So what we're going to do now is we're going to print w1. And we're going to say w.naught. And we have to index here the naught because when we return w in this line, that's a 1 by 2. So we take the 0th row of it, but we still have two elements in the column. So we need to say, okay, I want the 0th one for the first weight, and then for the second weight, we have to say I want the first element from that tensor, and then we have to say let's print our biases. So print b, and then print the value of b, our variable. And then what we'll do is say ax2.plot our costs. So we're going to plot our cost on the second axis. And we're going to plot them in blue. So B. So that's just an argument there to define what color. And then, so now we're going to compute our hypothesis surface for all the values in the input domain of the number of rooms and windows. So we're going to say our output hypothesis as a surface, this is the equation of a plane, is going to be b, so bias plus x1, which is a matrix we got from our mesh grid function, times the weight associated to the number of windows, plus x2 multiplied by the weight associated to the number of rooms. And then what we're going to do is we're going to plot that surface. So we're going to give it a name so we can create it as an object. So we're going to create a surface plot object on AX1. We're going to say plot surface. And we want to plot that surface along the first axis. We're going to have x1. Second axis we're going to have x2. Then we're going to have y, which is what we computed here. And we're going to say, okay, the color of that is equal to RGB values, and then the transparency. And to make it aesthetic, we're going to make this graph rotate as we're updating our plot. So we're just going to set the azimuthal direction view equal to the number of epochs by doing this. So we're going to initialize the view when we show this graph in the azimuthal direction, number of epochs. That doesn't really matter, it's just to make it look pretty. And then we're going to update what has been created by drawing on our canvas. So fig.canvas.draw. And then after we've plotted that first surface, we want to remove it after every iteration, so we don't end up with seeing every single plane that has been plotted over the entire history of each iteration. So we want to remove it after we've seen that one. So we want to remove S, which is our surface plot. That's why we created it as an object, so that we can call this function remove on it. And so the last thing we need to do as we're iterating through is to take a optimization step. So we're going to say optimizer.step. That's going to move our weights one little step in the direction which most reduces the cost. And so if we run that, so I've misnamed one of the axes up here, on line 35. So here, yeah, that should be axis AX2. So change that, then we'll run it. And what we can see is our hypothesis surface approach the exact fit of our data. And we can see how our cost has reduced over time, over iteration. Down here, we can see the values of our weights, which we can compare with what we put into the made-up equation at the beginning to see how they're approaching those values. And we can also see which epoch we're on and what's the value of our cost at that point. And so you probably noticed that the hyperplane doesn't converge exactly to the data, but that's because our optimization algorithm doesn't work very effectively for this one, and it's not the best one. So you can play around with changing SGD into different possible optimizers and see if any of those work better. But after we've run through this, however many times we specified, we should have an optimized model, right? And so what we should be able to do now is predict something from it. So let's have a go at that. So we'll say v for some variable is a variable that we're going to put into our computational graph to predict. So that's going to be a torch.tensor, capital T. And let's put in it, let's say it has 4 windows and 1 room. And now we're going to print our prediction of that. So our prediction of 4, 0 is going to be m.forward of v, and then we want the data from that when we print it. So we want the 0th row, the 0th column. So let's run that and see what happens. And what we've got from that is that our prediction of the price of a house with 4 windows and, so that should have been a 1, 4 windows and 1 room is going to be 8.27, whatever units that is. So let's change that because, yeah, that was meant to be a 1. And now the last thing we want to show you is to be able to print the state dictionary, so you can see after your model has been optimized, yeah, we can print the state. Oh, we don't need speech marks, do we? We just want to print the state dictionary of the model, and that'll show you all of the tensors stored in there. And then what we can do is we can save this model after we trained it. So we can do torch.save, and we can save the state dictionary of our model. And we'll save it as saved linear model. And that's it. I hope you've enjoyed the walkthrough of this. Be sure to play around with all the variables in here, try and break it, and teach yourself what makes it work and what makes it fail. And get ready for the next ML Wednesday.